we're going to work on optimization problems. That's where we have a situation where we need to maximize or minimize a certain word problem. In this problem, we have a manufacturer wants to design an open box that has a square base and a surface area of 108 square inches, as shown in the figure to the left, 3.31. What dimensions will produce a box with a maximum volume? Okay, so we're going to kind of think about what it is that we need to optimize. So we want, optimize means maximize or minimize. So we want to maximize our volume. To maximize our volume, that means our primary equation is going to be our volume equation. So the primary equation, that's the formula we're going to optimize. The formula we will optimize. I'm actually going to move that over there to the left or to the right so that I can write my primary equation right here. It's going to be volume equals the area of the base. Now the base is a square, so the area of the square is x squared, and then the volume we multiply times that height. So there's our primary equation. Now they give us some more information in the problem that's going to assist us. So the additional information is going to be our secondary equation. So our secondary equation, that's the one that allows us to solve for an unknown. Allows us to solve for an unknown that we need for the primary equation. So they're going to give us two pieces of information. One is the primary equation, what we want to maximize or minimize. So I'm going to highlight that in yellow. The primary equation is connected to whatever it is that we want to optimize. And then the secondary information, well, that secondary information is going to allow us to write a secondary equation. That's going to be the surface area. So the surface area of 108 square inches. Well, the surface area of 108 square inches is equal to x squared, right, plus 4xh. How do we know that? Because they gave it to us right over here. There's another way that we can find surface area. We can go back into our geometry knowledge and we can come up with that equation to find that surface area, but it's very convenient that they gave it to us right over to the left. Okay, so what is this going to allow us to do? Well, I can take that secondary equation and I can solve it. I can solve it for h. If I solve this for h, I'm going to get 108 minus x squared equals 4xh, and then I'm going to divide everything by 4x, and I get h equals 108 minus x squared all over 4x. And then that's going to allow us to eliminate one of the three variables in our primary equation. So we now have volume equals x squared times 108 minus x squared over 4x. And I'm going to multiply straight across I'm going to actually reduce my fraction, multiply straight across, and I'm going to get 108 x over 4 minus 1/4 x cubed. So this x cancels out with one of these x's. And then I can just distribute across. And then that 4 goes with both terms. And you can do that work off to the side if you want. You could do that work off to the side if you want. If you need help with that, we could always make another video. So I've got 27x minus 1/4 x cubed. Now this is a really nice problem because I have two variables. I have an input and an output. Now what is it that I need to do? Remember, all of this work was so that we could maximize volume. It was a little difficult to maximize the volume when we have three different variables going on in the volume equation. So that secondary equation allows us to eliminate one of those variables in our primary equation. So we've successfully got the volume is equal to an expression in terms of x only. Now I can find, I'm going to make myself a little note here. So now we want to find the first derivative, set it equal to 0 to find a max or a min. In this case, we have to find that maximum because we wanted to maximize the volume. So V prime is equal to 27 minus 3/4 x squared. I'm going to set that equal to 0. So when I set that equal to 0, I have 3/4 x squared equals 27. I'm going to multiply both sides by 4/3. And I'm going to get x squared equals 36. So I multiply both sides by 4/3 and I get x squared equals 36, in which case x would equal plus or minus 6. Now x can't equal -6 because can you have a -6 length? Absolutely not. So it's just the positive one. So we're looking at 0 to some other number, right? We don't know how large this could be. They didn't give us how large x could be, but x could get pretty large. So I'm going to say infinity, even though you can't have it be infinity, just to show you that it could keep going. We could make this a huge box that could take over, gosh, the entire neighborhood. So now what I need to do, remember, is my first derivative test. So I need to check a value between 0 and 6 and put it back into the first derivative and see if we have a positive or a negative. So when I put a 1 in for x, I get a positive. So that means my function is increasing between 0 and 6. 6 to infinity, if I put a 7 in, guaranteed I'm going to get a negative. You can check the work though. So therefore, at x equals 6, we have a max. So what are the dimensions? Well, the dimensions are x by x by h. If x is 6, I'm going to have 6 inches by 6 inches, and then what would h equal? Well, h is 108 minus x squared all over 4x. So h is going to equal 108 minus 36 all over 24. 108 minus 36 is 72, and 72 divided by 24 is 3. So our dimensions are 6 by 6 by 3. So let's go through this again. We've got our primary equation that comes, it's a formula that comes from whatever it is that we need to optimize. So we need to optimize volume. So volume is going to be our primary equation. Our secondary equation is some other piece of information in the problem that's going to allow us to write an equation and solve for a variable that we can substitute back into our primary equation. Our goal is to have our primary equation have two variables, an input and an output. This way we can avoid having to do implicit differentiation. Okay? Once we use our secondary equation to solve for a variable to plug back into our primary equation, we can then set that primary equation equal to that derivative equal to 0. Okay? So let me get a little dot here and let me show you where I'm at here. So now after we get our secondary equation solved for h, we plug it back in, we can come over here and we can manipulate that equation so it's in a nice form for us to find our derivative. We find our first derivative, set it equal to 0, right? We set it equal to 0. There we go. And we solve for our critical numbers. Now, -6 was outside the feasible domain because -6 can't be a dimension in our primary equation. Therefore, that critical number doesn't apply here. So we're going to use our +6 only. So our feasible domain starts at 0. Potentially it could go up to infinity, but realistically it would never reach infinity. Otherwise you would never really have a box. You get it. Okay, then we test positive, negative for increasing to decreasing. Increasing to decreasing means that at x equals 6 we have a maximum. So at x equals 6 we have a maximum. Hooray! That means that x equals 6 right here, 6 by 6. How do we find that h value? We can plug that 6 back in for x into our surface area equation, which we manipulated to be h equals 108 minus x squared divided by 4x. We could have easily put it into this one as well because it's the same equation, it's just not solved for x. And then we got our dimensions. So hopefully that was a nice little quick review of that. Here's another example that we're going to do, finding a minimum sum. Okay, we're going to find a minimum sum in the next problem. So I'm going to start another video for that next problem. Each problem is going to be its own video so that you have time to absorb.